Hi, everyone. In this lecture, we are going to look at non-determinism and this class called NP, which is like an analog for the class P that we saw in the previous lecture. So P corresponded to the set of all languages for which we could design efficient algorithms or polynomial time algorithms or polynomial time Turing machines. Um, and yeah, we saw that we could do this for quite a few languages. Okay, but there are many other problems for which we don't know if this is actually possible. So we don't know polynomial time algorithms or efficient algorithms, and we might discover it in the future, but we don't know yet of any efficient algorithms for them. Okay, and many of these natural problems belong to a particular class called NP, which will be the focus of today's lecture. Okay, so and this will have a lot to do with non-determinism as well, as we will see. Okay, so here is an overview of the lecture. Okay, so we'll first revisit non-determinism in the context of non-deterministic Turing machines. Okay, and then we will define this class called NP, which is analogous to the class P that we have seen in the previous lecture. And then we will then give an alternate definition or a characterization of NP in terms of something called polynomial verifiability. Okay, and finally we'll end with the big question, which is perhaps the most central question in computer science, which is the P versus NP question. Okay, so first let's do a recap. So let's continue and let's do a recap of non-deterministic Turing machines. Okay. So non-deterministic Turing machines are very much like standard Turing machines. Okay, except that the machine can proceed according to several possibilities. Given a particular state and the input symbol and so on, there can be multiple possibilities that the Turing machine can take, and yeah, so machine can proceed along these different possibilities. Okay, and the non-deterministic Turing machine accepts a string. Okay, if there exists an accepting path. So this is very much like a is very much like a non-deterministic finite automaton, except that this is just the same in the context of Turing machines where you have a tape as well. So there should exist a path from the starting configuration or a sequence of moves from the starting configuration to an accepting configuration. Okay, good. There might be multiple sequence of steps that you can take as long as you have one sequence of steps that go from the starting configuration to an accepting configuration. That particular input is accepted. Okay, so the non-deterministic Turing machine will also be represented by the usual 7 tuple. Okay, and you have the usual set of states, the input alphabet, the tape alphabet, and then the transition function, start state, and the set of accepting state and the reject state. And the main difference is in the transition function. Okay, this transition function, as opposed to a deterministic Turing machine, this transition function this is just a recap. Okay, so you can go from a state comma input pair to a bunch of possibilities. So this is represented as a power set. Okay, a set of possibility. A set of possible moves. Yeah, okay, good. And just to kind of pictorially keep this in mind, in a deterministic Turing machine, you start with some start state, and then you take a bunch of transitions given by the input and so on. Okay, so initially you start with Q0 and some input W. Okay, and then you take a bunch of sequence of moves, and finally you end up at some configuration which is either an accept or a reject. Okay, we are mainly looking at decidable problems, so we can assume that the Turing machine always accepts or rejects, versus a non-deterministic computation where you can start out with this configuration of initial state and input, and then there might be multiple possibilities. So maybe the first step is fine, but then you may start seeing multiple possibilities, and in turn you may see multiple possibilities here and so on. Okay, and some of these could be accept configurations, some of them are reject. Okay, now let's go a little more into detail about accepting configurations. Okay, in particular, let's define what is an accepting configuration history for the non-deterministic Turing machine N that we have defined here. Okay, on input W. So an accepting configuration history is a sequence of configurations. Okay, so let's call them C0, C1, C2 up to CT, where C0 is the start configuration. Okay, so for instance, here it's the starting state is Q0 and the string is W. Okay, CT is an accepting configuration. And finally, each configuration CI yields CI plus 1, okay, from a valid move, from a valid transition. Okay, so if there is such an accepting configuration history for the non-deterministic Turing machine N on input W, we'll say that N of W accepts. So N accepts W in time T. Okay, because it goes from C0 to C1 up to CT, so it's T time steps. Okay, so basically N of W accepts in time T means that such a accepting configuration history exists. Okay, good. So now, just as we defined time complexity of a deterministic Turing machine, we can also now define the time complexity of a non-deterministic Turing machine. Okay, in a very similar way, we'll say that N has time complexity T of N. Okay, if for all input size, for all N, okay, that is, so for all N and for all inputs of length N. Okay, so N here is a natural number, okay, of length N and all histories, whether accepting or not. all yeah, all histories, and then so n halts in t of n time. Okay. So the set of configurations that it goes through, that is the history, configuration history or computation history. And for any input of size n, the set of all possible computational histories should really end within t steps, t of n steps. So the non-deterministic Turing machine halts in t of n time. I mean, whichever configuration history or computation history you look at. Okay, whichever of the many different paths it can go through. Okay, and this is not really a big restriction because we are looking at decidable problems. You can always make the non-deterministic Turing machine halt in t of n steps, okay, like a clock. Good. So this is the definition of time complexity for a non-deterministic Turing machine. And just like we did with deterministic complexity classes, you can also define non-deterministic complexity classes. So, let's say n time t of n is just the set of all languages such that L can be decided by a non-deterministic Turing machine, okay, which takes order t of n time. Okay, good. So now, if you compare the two definitions, it's easy to see that the complexity class time of t of n is certainly a subset of the non-deterministic time complexity class n time of t of n. Okay, and why is this? That's just because any deterministic Turing machine is also a non-deterministic Turing machine. Okay, now here is a question that is quite open. Okay, is this a proper containment for all t of n? Okay, and this is still quite open except for some corner cases. Okay, good. So the next question you may ask is, well, what kind of problems can be solved efficiently using a non-deterministic Turing machine? Or what kind of problems can be solved efficiently non-deterministically? Okay, and now let's see an example. We look at what are known as Boolean formulae over Boolean variables. This is something that you may have seen in a discrete mathematics course or a computer logic course, digital logic course. Okay. Now, so a Boolean formula will have a bunch of variables. These are Boolean variables. Let's say x1, x2, and so on up to xn are Boolean variables. Okay, a formula can involve things like it can involve some of these variables. You can involve negations of these variables. So this stands for not. This is and this is or. Okay, so you can have something of this form: not of x1 and x2, or x3 and not of x3. Okay, and so on. Okay, good. So you can also have brackets that tell you what's the order of operations to be done. Okay, We'll say that a Boolean formula is satisfiable if and only if there exists an assignment, a satisfying assignment for it. Okay, so by that I mean a satisfying assignment for each of the variables so that the formula is satisfied. So for instance, okay, if you look at the formula given by x1 and x2 and not of x3, okay, versus if you look at another formula that's given by, maybe let me look at something a little more interesting, x1 or x2, okay, and then not of that followed by and of x2. Okay. Now, this is a satisfying assignment. It is a satisfiable formula, okay, because you can think of the assignment x1 equal to 1, x2 is equal to 1, and x3 is equal to 0. On the other hand, if you think about this for a bit, this is not a satisfiable formula because if you take x2 equal to 1, there's no, yeah, I mean, if you take x2 equal to 1, then this this part is satisfied. So it's something and x2. So that means x2 has to be 1. But if x2 is 1, the first part is not satisfied. Okay, good. So this is not a satisfiable formula. Good. So SAT is now a language. Okay, so this is just a set of all is a satisfiable Boolean formula. Okay, the set of all satisfiable Boolean formula constitutes the class called SAT. Okay, now a particular subclass that of SAT that might be particularly interesting to us comes from Boolean formulae of a restricted flavor. Okay, and this subclass of Boolean formulae is called 3CNF. Okay, the name sounds like, I mean, it is an abbreviation that stands for conjunctive normal form. You don't need to remember the abbreviation, okay, but it's just a very, very useful set of subset of Boolean formulae that we'll also encounter a lot in this class, particularly in the next lecture. Okay, so this consists of it consists of Boolean formulae of a specific form. Okay, so you can, for example, you may have something like this: x2 and maybe not x1 and not x2, sorry, or not x2, or x3 and maybe some x4, or x1 or x6 and x3, or not x5 or not x2, and so on. Okay, so the thing to notice here is that a 3CNF formula is an AND of a bunch of expressions. Okay, it's an AND of a bunch of Boolean formulae, and these individual formulae are called clauses. Okay, so it's an AND of a bunch of clauses. Each clause is an OR of either the Boolean variables or its own negations. So these kind of things. So these particular things, where it's either a variable or the negation of the variable, these are called literals. Okay, and so a 3CNF formula is just an AND of a bunch of clauses each of which is an OR of a bunch of literals. Okay, that's a Boolean. I mean, that's a 3CNF formula. And now 3SAT is just the set of all 3CNF formulae that are satisfiable. Okay. Okay, so now let's see. So 3SAT is a language, and let's see a non-deterministic Turing machine for 3SAT. Okay, an efficient non-deterministic Turing machine for 3SAT. Okay, let me actually just copy paste it here. So this is a very, very simple non-deterministic Turing machine. First, given a formula phi, okay, we just on input, okay, this is on input. Formula phi, okay. So given on input a formula phi, we'll just first check if it's a valid 3CNF formula. And this just requires a scan, okay, you know, a linear scan, okay, over the whole input. So let's say that this is a formula of on input a formula of size n. Okay, that means the whole description of this Boolean formula, you know, the Boolean formula can be described using an n-bit string. Okay, so this includes all the clauses, the yeah, I mean how the clauses are composed of the different variables or literals and so on. So you can check if it's a valid 3CNF formula in just order and time, because you just need to check if you know it's an AND of a bunch of ORs. Okay, and each of these consists of exactly, each of these clauses consists of exactly 3 literals. So you can just go 3 at a time and check that it's valid. And then, you know, how are you going to see if it is satisfiable or not? Well, for each of the Boolean variables, we are going to non-deterministically substitute either the value 0 or 1. Okay, and now we'll just, this will give you, if you non-deterministically guess a value for each of the variables, then this will give you an assignment, and you just check if the assignment satisfies phi. Okay, so both of these steps, this is a non-deterministic step, which is order n time. This is also order n time. So in total, this is an n time of n. So 3SAT is an n time of n. Okay, because testing if the assignment satisfies phi is just a, you know, you just need to check if all the clauses are satisfied. Okay, that's again just a scan. So if the formula is satisfiable, there is a valid assignment, and that is something that you would have guessed non-deterministically. Now, if for all guesses it is not, I mean, in none of the guesses, that is none of the assignments satisfy phi, then it is not a satisfiable formula. And so, you know, you correctly reject that formula. Okay, so this is an n time of n. And there are many other natural problems. In fact, most natural problems that you can think about, as we will see in a bit, will actually fall into this class NP. Okay, so now, just like we defined P, you can also define the non-deterministic analog. Okay, so this is the notion of non-deterministic polynomial time. Okay, so we'll define NP to be just the union over all natural numbers k, okay, of n time of n to the k. Okay, so this is just, I mean, basically this is just the the non-deterministic counterpart of P, which is just doing the same thing for deterministic Turing machines. Okay, and this is why the complexity class time of n to the k is also sometimes called d time of n to the k, because that's deterministic, and you want to distinguish against a non-deterministic um, um, counterpart. Okay, so NP is the set of all languages, okay, that can be decided using a non-deterministic Turing machine that takes only polynomial time. Okay, so NP really stands for non-deterministic polynomial time. Okay, and I mean, there's this misconception that NP stands for not polynomial time, and that's certainly not the case. NP just stands for non-deterministic polynomial time. Okay, good. So, but here is a slightly different um, uh, way of defining the class NP. Okay, so this is a theorem which actually also gives you an alternate definition of NP. And this is actually, I mean, in many ways, this is a more natural or a more natural way of reasoning about the class NP. And is very, very useful to think about it in this context. Okay, so think about it in this way. So we'll say that a language L is an NP. Okay, if and only if, so I mean, this is, sorry, this is not a definition, this is a theorem. L is an NP if and only if there is a polynomial time Turing machine, which we will call V, okay, which stands for verifier, okay, and a number k, an integer k, a natural number k, such that L is is precisely, L can be written as the set of all x such that there exists a y is just a string with the size of y being at most the length of y is at most the length of x raised to the power of k. So k is this integer that's defined beforehand, and v of x comma y accepts. Okay, so let's just go over the statement a little bit. Okay, so we're saying that a language is an NP if and only if you can actually design this efficient polynomial time deterministic Turing machine V. Okay, so this is a deterministic Turing machine. Okay, and a number k, an integer k, is such that L is precisely those strings where for every x, for every x in L, you can come up with a string y whose length is at most the length of x raised to the power of k. Okay, such that this polynomial time Turing machine V will accept x comma y as input. Okay, and L, I mean, if you can construct this polynomial time Turing machine V such that L is precisely those strings x for which there exists the string y, which is polynomially bounded, and V of x comma y accepts, then L is an NP, and vice versa. Okay. Good. Okay, so now let's prove this. Fairly simple proof. Okay. So let's do the first part. That is, if L is equal to the set of all strings x such that there is another string y, which is of not very large size. It's not a very long length. Okay, and v of x comma y accepts. Okay, then we want to say that L is an NP. Okay, so how do we do this? Well, remember that V is a deterministic Turing machine. Now, what we're going to do is we're just going to non-deterministically guess. Okay, so this is the first part. Okay, so um, So we're going to non-deterministically guess y. Okay, and we're just going to run v on x comma y. Okay, remember that this is a deterministic TM. Okay, so and that's it. Okay, so this actually is the construction of a non-deterministic Turing machine. Okay, so this is the non-deterministic Turing machine. Okay, it's just going to non-deterministically guess y, and it's going to run v of x comma, I mean v on x comma y. Okay, and if it accepts x. Otherwise, it does not accept x. Okay, so if for no value of y, um, if for no guess it is v of x comma y accepts, then it's going to reject. Okay, so this is a valid non-deterministic Turing machine. Hence, L is an NP. Okay, and the key thing to see that it is an NP is that V runs in polynomial time for all guesses of y. And remember that since for all guesses y, since the size of y, remember, is at most the size of x to the k. So this is at most n to the k, and v is going to be polynomial in the n to the k, which is also a polynomial. Be some non-deterministic Turing machine deciding L. Okay, now we just define this deterministic Turing machine v of x comma y to accept if and only if y is an accepting configuration history or computation history for n on input x. Okay. Now the main thing to note is that checking if y is an accepting configuration history is quite simple to do. It's actually going to be just if you remember what accepting configuration history is, it's just a sequence of configurations. Okay, where the starting configuration is going to be the start state comma w, and then each CI yields CI plus 1 through a valid transition or valid move, and then you finally have to reach an accepting configuration. So you just need to go and check if each of these successive configurations correspond to a valid transition or move. Okay, and this just requires going through each of these configurations and checking that they're valid. And you start from C0 and you end up in a valid accepting configuration. Okay, so this can be done efficiently. And so now, okay, so this is hence so this actually concludes the Turing machine that we need, and this shows that you can actually write it in the same form. Okay, so L is also, this says that L is the set of all x's such that you can come up with a y which is not too big. Okay, that corresponds to the configuration history such that v of x comma y accepts. Okay, and y small? This is okay. Just to elaborate a bit more on it, y is y small. Y corresponds to the length of y. Okay, corresponds to the time. Okay, and we know that this is polynomial because it's an NP. Okay, so y is also small, and so this gives you what you want. Good. So you have this alternate definition of the class NP. I would say that the main takeaway is this alternate characterization or view of NP. Okay, and okay. So you can say that a language L is an NP if and only if there are polynomial length uh, proofs or certificates of membership. Okay, for L that are verifiable efficiently. Okay, so the string y. So so you say that X is an L if and only if there exists a string y. The string y is often called the certificate or the proof. Okay, for membership of X in L. Okay, and not only do you need to produce this proof y, you also need to check that. I mean, there is some efficient procedure, which is this Turing machine V, that that can look at X and Y and tell if I mean, that accepts based on whether Y is a valid proof or valid certificate for X. Okay, so good. So those languages in NP are exactly those languages for which there is like an efficient or I mean efficiently verifiable proof of membership. Okay, so for example, 3SAT. Okay, so let's just write down 3SAT in a way that makes it clear that there is such an efficient certificate. So it's just a set of all formulae phi, Boolean formulae, I mean, which are 3CNFs, such that um, phi is a, so it's, let me write it this way, phi is 3CNF, okay, such that there exists a y, okay, such that y is a satisfying assignment to phi. Okay, so the fact that phi is a 3CNF formula is easy to verify. Okay, and in fact, if you want, I can naturally write it here. Okay, that can be easily verified. But yeah, so it's those are 3SAT exactly corresponds to those 3CNF formula such that there is a y which is a valid satisfying assignment. So y is this proof that the formula is satisfiable. It's just a satisfying assignment. Okay, so 3SAT is an NP. We already saw that it was an NP, but yeah, I mean, there's an easy way to see that it's an NP. And most natural problems that actually you would encounter are actually in NP. So some examples are clique. These are problems that you might see in a future class, or in the algorithms class, or Hamilton path. Okay, and in fact, many of the problems that we'll care about actually fall into this class NP, because these are the problems for which, even if you have a solution, I mean, you should be able to, I mean, the basic requirement for computational problem that I mean you may care about is that when you see a solution, you should be able to verify that it's a solution. And NP exactly captures all those problems. Okay, good. So let's just recap what we have seen in the last two lectures. Okay, so P is the problems, the set of all problems that can be efficiently solved. Okay, by efficiently solved, we mean solved in polynomial time. NP is the set of all problems where proposed solutions can be verified efficiently. Okay, and the $1,000,000 question is the class P equal to NP? Okay, it's literally $1,000,000 question because this is one of the 7 millennial problems that were identified by the Clay Institute. Okay, um, and it's a profound problem with many philosophical implications. Okay, but let's just again see what it is. So P is the set of all problems for which we do have polynomial time algorithms. So this is a notion of efficiency. You can solve it efficiently. NP is a set of all problems where given a solution, I can verify, proposed solution, I can verify if it is efficiently whether it is a solution or not. Okay, you can identify a solution efficiently. Or, identify a proposed, verify a proposed solution efficiently. Okay. Now the P versus NP question basically asks, well, if you can verify a proposed solution efficiently, can you also find one? Okay, so it's so it's related to things like, can problem solving be automated? Because if you can verify a solution to a problem efficiently, can you in fact can you actually go ahead and find a solution efficiently? Okay, and it also has many other, if P is equal to NP, it will have major consequences. Uh, profound consequences. Like you can automatically prove true theorems, true statements. Uh, it is also related to things like automating creativity because, NP really captures all those things where that you can recognize or appreciate. Okay, and a solution when you're presented one. And if P is equal to NP, then you can also find it yourself. Okay, and if P is equal to NP, then some of our basic the underpinnings of the problems that are really the underpinnings of modern day cryptography will have efficient algorithms. So there will be no cryptography. Okay. On the other hand, we do believe, this is a conjecture, and many people believe that P is not equal to NP. And this will also actually give you a lot of insights. Okay, so this will tell you that there are problems that are fundamentally computationally hard, and such problems will actually do actually have a lot of use. For example, in cryptography, in applications like cryptography. Okay, and more importantly, it has it's a fundamental interest in computer science to understand whether there are these kind of computationally hard problems, okay, for which you can efficiently verify solutions, but can you find them efficiently? Good, I'll leave you with this problem, and thank you. This concludes the class on non-determinism and the class NP and the P versus NP question.